Okay, so good morning. So we begin a new chapter in classical mechanics, and so okay, and we'll just call it non-inertial frames. Okay, so before that, let us recall what an inertial frame is, right? We did this in the beginning of the semester. So can someone remind me? I mean, so you should have. So the whole idea here is there are So actually, I prefer not to talk of a single frame. So we'll let us consider. Okay, so instead we will talk about mutually inertial frames. Okay, so these are related to two observers. Okay, or equivalently two observers. So how did we work out? So how are two inertial frames related with each other? What is the transformation?
Galilean transformation.
Okay, so good. So now let's sort of so let's assume that there's an observer O. So that person picks an origin, also picks a right-handed triad. I'm going to define it in this fashion. So for instance, so this person, so would so position or displacement with respect to this thing. So you will write that as x vector, or okay, let's write it as x vector is equal to. I don't want to write. I'll write it below because I want to draw something else. Okay. Okay, so this is what we would do, right? We would expand any vector in this fashion, and so we will either think of it as in this fashion, in this form, or this triple, right? It's a triple or a triplet of numbers. Okay. So first thing is the second observer need not be choose the same origin, so that will happen. So let's do one thing. Let's try to join these two guys by some vector, and we'll call this the R vector. Okay, so their origins don't match. Further, this person will choose a slightly different frame. No reason. Okay, so say so there is some point P. Let's say this is a point P, and then okay. So this person would measure would write for the same point P, this person would choose some coordinates, so they'll assign. So let's write that here. I can write it next to this, so I'll just write it's a different. Go back to the white color. So this person will write x1 prime or a triplet, which is right. So these would be the coordinates of the point P in the frame O prime. And so we saw that a Galilean transformation would take the form. So, and we always wrote it like this. We wrote it in terms of xi primes equal to some rotation matrix. So let's say call it R, Ij, Xj plus. Okay, let me just use lowercase letter here because I use capital R for something, right? Plus then Ui T plus some shift of origin, which we will write as some x naught. Right, so these were three parameters here. Okay, and there's also t prime. So and they also have a time. Is t prime equal to, say, let time is matched up, but we could have a shift. Right, so this was the general Galilean transformation. Okay, so this was the picture. So is this clear? This is what we had written. Okay, so now what we're going to do is let's look at this and try to understand what this R vector. What should R vector be?
A rotation matrix.
No. This R vector, O prime.
I'm sorry.
Yeah. So it's what is the origin in? So we want to ask what is the origin in the x prime basis. So we want. So what am I trying to ask? Okay. So all I'm saying here is that we want O prime. What would be? So this would be the instant. So this is where the origin of this will be located in the xj frame. Okay. So what I want to say is that up to some sign, this is the term which is like the. So you look at this. What it says is that O prime is moving with velocity minus u, I guess, with respect to O. Right. The origin is moving away. So the observer O will say that O prime is moving with velocity ui minus ui, right? Minus u. And this is just some the initial at t equal to 0. There, that is the vector which gives this thing. So right now we're not worrying about time. So that is so this R is out here, but we can also understand the following thing: ei prime, okay, is equal to R inverse or R transpose is a rotation matrix of Ej. Okay, and it's easy to show because really what is happening is that how these two guys should cancel each other. So what I'm saying is that, yeah, so that's what I want to say. So is this point clear that this rotation matrix is coming because they have not aligned their axis, right? Is this point clear?
Yes, sir.
Okay. So I just put that inverse here, which is also recall that R inverse equal to R transpose. Because it's orthogonal, special orthogonal, but orthogonality is all we need. Okay, so this is what we have. Okay, so now, so this is the, so here we are looking at how the coordinates are changing, which is a very active picture. That's also a passive picture. Okay, so the passive viewpoint. And this is generally preferred in the math literature. While in physics, we know when we say the vector, we assume there is a basis chosen, and those are the components of that. Okay. So what is written out there is the following: is that x vector. So they say that. So I'll just write something and then. Okay, summation over I should write. This should be equal to summation over I xi prime ei prime plus some r vector. Okay. So in the passive viewpoint, the vector here, the vector is unchanged. Is this clear? So the vector is unchanged, but the components will change.
Sir, how are you adding the r vector for this?
Yeah. Okay. So the point here is that this change. So there are two aspects to choosing a frame. Okay. One is choice of origin. Okay, and then you choose based at that origin, I'm going to choose a frame, orthogonal frame, and I'm assuming Cartesian for simplicity.
Sir, but I mean this xi ei prime is just the dot product, and it has to be constant in different systems. Why is the r required?
Because the origins are not the same. So x equal to 0 and x prime equal to 0 are not the same points.
Xi ei cap is not the dot product, Siddharth.
It is not. It is actually. It's absolutely right. It's not a dot product. It's a wrong statement. Yes, thank you. It's not even a dot product. It's just a statement that a vector this thing can be expanded in some basis. That's all. Thank you. Yeah, it's not even dot product. It's wrong to say this is not a dot product. Okay, because see, I mean, so a dot product would be involving two vectors. Okay, in some sense, xi and ei are not vectors. I mean, one of them transforms like a vector, the other transforms with a transpose, right? So they cancel. Okay, that's what I was using here. That's what I'm saying here also.
Okay. Sir, is x the position of a random point?
Yeah, so there is a point. So here is a picture. So let's look at this picture. In frame A, origin is O, and axis is E1 prime, E2 prime. Okay, it's a global, global frame. That's a point P. I picked that point. Okay, so what is the numbers that this observer O will associate with it? X1, X2, X3. By expanding in their own basis. Okay.
Yes.
What will O prime do? Expand in their own basis and call the same thing, write this. Correct?
Oh, yes, sir, I get it, sir.
Okay.
Yes.
Sir, why ei prime is R inverse ij? R inverse ej? Why not R?
Because that is the point. Very good, very good, good. The reason is that is that this quantity, this thing is invariant. Okay, so if xy prime, if you wish, you could do the following thing. You can change. You can choose take the same origin and choose a different basis. Okay, and ask how do these things transform. Okay, so in the same frame, you keep O prime as the same origin, but so let's even here we can do this. Take R equal to 0. So they have agreed on the origin. Okay.
Okay, sir.
then right, so the vector is not changing. You're changing the basis and its components are changing to compensate. The vector is the same. Point P is not moving.
So this statement is true only if X is like a position vector, right? It is not true for any vector.
At this point, that's all. So when we say what is a vector under what, you have to ask, okay, under rotations. Okay, what is it under Galilean group is more complicated. Okay, so
Sir, here X is written in two different bases at the same time, AI and AI prime.
Yes. So the frame has two quantities. One is the position of the origin, and then there's also the fact that we can have rotations in frame.
So here there are 6 components.
For what?
For X vector.
No.
EI1.
Each person, no. Each observer will associate only 3 numbers. Observer O will say x1, x2, x3. Observer O prime will say x1 prime, x2 prime, x3 prime. Nothing more.
Sir, R vector is in X EI basis. So, and here the first term is EI prime basis. So, two different 3 and 3.
Huh? R vector is some constant vector.
Some constant.
Which is a property of the two frames. So if you come back here and look at this, you change P, R is not going to change.
Okay, sir.
So R is the relative thing between the two frames. Okay, so if there was only one frame, observer O prime will never bother about R unless he or she wants to connect up with observer O. Okay, then you need this. Because x prime equal to 0 is not x equal to 0, right? xi equal to 0. That's all. Okay, so this is important. Okay, this formula is kind of nice, and so at this point I'm only doing position vectors, and okay, so is this formula clear now? What I've written. This is the passive viewpoint. The point doesn't change, the vector doesn't change. Okay, but you are doing stuff. Okay, so this is what we have. So so you can see that the story of you can write the whole Galilean transformation story in the setup by realizing that this is some R of T in some sense, and this rotation matrix is how the two bases are changed related to each other. Okay, so that's what. So it fits into this framework. It is not okay. So the idea is that so the point here is that in the two mutually inertial observer agree on forces. Okay, so if one person says F equal to 0, it's true for both. Okay, this is how we worked out R, but we want to go beyond this. Okay, so we want to go okay, so we want to look at situations where observers do not have to agree on forces. Okay, in other words, consider situations may not agree on forces. Okay, so F equal to 0 in one frame does not imply, not may. F equal to 0 in other frame. Okay, So I'll show you in a moment how this will come about. Okay, so is this point clear? So we want to do this, and so now for simplicity, we will focus on the situation where the two observers agree on origin. Okay, that means this implies that r equal to 0. It's very easy to put back r equal to 0. Okay, r not equal to 0. We'll do that. Okay, is this clear? So here in this case, one has okay, because r equal to 0. Okay, so let's do one thing. So we will we'll make okay. So let us choose a time dependent frame for O prime. So what I mean by that is ei prime is a function of time. Okay, so is this point clear? But we will assume that ei's are constant vectors. Okay, so O. Okay, and that there is no time dependence. In the frame O. Okay, so what is happening is as time changes, what you should do is think of these, so this is some triad, right? Right-handed triad. This right-handed triad is rotating. Okay, classic example would be, for instance, if we chose one example where this would happen is if you work not in Cartesian, but say you worked in spherical polar, and you know that as you move around, spherical polar basis changes from point to point, right? So if there's a particle and we are trying to choose a basis which is aligned with the spherical polar coordinates every instant, it will be as the particle is moving, this will rotate. So you will get some time dependence. It's possible. Another way you could get is if you have, some you have a frame attached to some rigid body and that is doing some wobbly motion. Okay, so you can think of some fixed frame on the rigid body, and the body is rotating in weird ways. So even the frame will keep rotating. Okay, is this point clear? So we want to study how. So what do we know about ei prime? So what we know is that ei prime of t is a right-handed triad of orthonormal vectors, right? It's a basis, orthonormal. Okay, so in particular, there are two properties. First property is orthonormality, which is ei prime of t dot ej prime of t. What will this be equal to? Anybody?
0.
Delta ij.
Delta is
Okay, depends. I didn't say j is not equal to I, right? Okay. Second one says that I'll just write it for one of them, E1, but I can write it in more general form. What is this equal to?
E cap 3.
E3.
E3 cap T.
Thank you. So this holds at all time. Okay, holds at all times. Okay. So
Sir,
let's.
what is the name of the second equation.
It's
First
just
one
a
is
right-handedness of the coordinate, right? Right-handed. So E1 cross E2 is E3, E3 cross E2 is, sorry, E3, 1, 2, 3, E3 cross E1 is E2, so on, cyclic. So more generally what we have to say, right? Okay, so it's, this is a more general statement, okay? And it holds for all times. So this we know, okay? So this is, you can see that this, so what I want to show is that we will associate a vector with such a thing. Okay? And this vector will be identified with the angular momentum of the frame. With the, no, sorry, what do you want to say? Angular velocity. Okay? So what we're going to do is let's take property 1 and differentiate it with respect to time. Okay? So take time derivatives of 1 and 2. So for 1, we get should be equal to what?
Zero.
0.
Right, something like this. Correct? That's what we get. Okay, so let us look at this first equation. So we'll call, okay. So you could take I equal to J. Okay. So what we get from this, it just says that we get dEI prime by dt dot EI hat prime equal to 0. No summation over I, of course, here. What does this mean?
So the ray,
Motion is
it's perpendicular to the.
Yeah, exactly. So, I mean, it makes sense, right? You think about it. It's a unit vector. So if you go along the same direction and then your only normalization will change, again, you bring it back, it comes back to itself. So it makes sense that it will not change in the direction. So it will be orthogonal to it. This is true for all of them. That's what it says. Okay. So in particular, for instance, if you have E1 prime of T, okay, so that would be some, let's say some coefficient. Let's call it beta 1 or rather beta 2 E2 prime. I can expand it. Okay, so there'll be only two parameters, and these can also depend on time, of course. Beta 2 and beta 3, they're not constants, just can vary with time. Okay, and so similar equations. for E2 prime and E3 prime. Okay, so how many coefficients we'll have? We'll have like 6 parameters, so 6 free coefficients. So we get. But we have 3 additional equations because 2 implies this was for only E1, E2. So there are 2 more equations. Okay, but 2 implies more conditions, 3 more conditions. Okay, so implies 3 free coefficients. Is this clear, my counting? So we got 6 from just imposing 1, whatever 1 said, right? Is that clear? No, there might be other, so there are few, still there are more conditions, but at least just imposing I equal to j, it's an I not equal to j also has some conditions. But anyway, at least, so you'll see that it's consistent with having 3 more conditions. Okay, so it's for you to work out what the details are. So please go ahead and put all of them in and see what it means. Okay, so I'm going to give an exercise. Okay, show that. Okay, so the 3 free coefficients where omega is a vector that knows about the time dependence of the frame. Okay, and of course omega in general is a function of time. I mean, I'm not saying it's a constant vector. Okay, is this clear? So this is just a claim. Okay, so this is an exercise. I want you to prove it. Okay, so is this clear what I have done? It just defines omega for you. I claim this is the most general solution to these equations, these 2 equations. Okay, it's easy to check, at least converse. It's easy part to check that whatever, for instance, you come here, you can see that, for instance, that this right hand side is always perpendicular to EI prime, which is exactly what we had there, right? That's what's one statement. And then you can also check that the right-handed thing story follows. Okay, so both things you can check, and that works. Okay, so it's easy to check one way, but starting from those conditions to show that it is this way is a little bit more work. Okay, is this clear? At least a claim statement of the claim. Okay, so let's.
Yes, sir. But just one question:
Go
omega
ahead.
may or may not be a function of time, right?
It depends on the case. No, but generally it is a function of time. There's no.
Yeah, generally it's a function of time.
There will be special cases. We will see now an example of a special case. Okay, where it is, where you can, it's constant.
Rotating.
Yeah, it is, but that's very special.
Yeah.
Okay, so what I'm saying here is both these right-hand side terms depend on time in general. Okay, so let's do an example.
So, sir, we said that the derivative of E1 dash equals to beta 2 E2 plus beta 3 E3 dash. So, in other words, we are saying that either beta 2 or beta 3 is 0 and
No, we are not saying that. No, we are not saying that. There are 6 numbers, but they are determined in terms of only 3. There are equations which will make them functions of each other. I'm not saying beta 2 is, that does not imply beta 2 is 0, beta 3 is 0.
No, I mean in the exercise we are claiming that d by dt of ei dash equals to omega cross ei dash.
No. So let's look at so before we do that example. Let's put I equal to 1 in that. Okay. Shall we do that?
Okay.
Okay, and let's expand omega in the prime basis only. Okay, substitute it there. So omega cross E1 prime, sorry, omega cross E1 prime, yeah, that's what we want, will be what? So we'll get omega 2 into E2 cross E1 prime, which is 1, 2, 3, 1, 2, 3. So 2, 3, 1. So it's minus omega 2 E3. Yeah, plus E3 with this. So E3 cross E1 plus omega 3. Okay, so now we can compare with that and we can see that this implies that beta 2 should be omega 3. Okay, and beta 3 must be minus omega 2. It's not saying anything is 0, right?
Yes, sir.
Okay, but if you did the other things, you would have a new coefficients, but you need to check that they all agree with this. Okay. So now let's do our example. Is it clear? Did I answer your question?
Yes, sir. Yes, sir.
Okay. So the example is the following, where now I am expanding E1 prime and giving its time dependence through the fixed basis, which is the O basis, which as we said is maybe I should put a minus sign here, I think. Let's keep it this way. Okay. So what is this? This is like...
why are you putting primes on the E2 caps?
Because I messed up. Thank you. Yeah, thanks. Yeah, now it's okay? Okay,
Yes,
so
sir.
now if you think about this is like the origins agree. So it's as if there's a turntable rotating with angular velocity omega, right? This prime, so it's like you have a record, like the old-fashioned, record player, where you put the LP or whatever, they'll rotate at 33 RPM or 45 RPM or 78 RPM. You guys are too young to know that, but you know what a record player is, right? They used to put that disc on top, it'll start spinning and there'll be a needle. Okay, so it's like that, right? So the prime coordinates is on the turntable. It's somebody on the turntable. And omega we'll associate with this thing. Okay, so from this, let's just do this. So let's look at this. So here, angular velocity. You can even put a prime. Right? It's like a angular velocity in the z direction. So you just have to go back and do d by dt of this and go ahead and check what you get. Okay? So please go ahead and check that this omega that you get for this is exactly fits this formula. Okay? Maybe there is a sign problem. You figure out. Okay, I won't do that. Okay, so verify that okay. What I am trying to tell you here is, at least for this example, you will agree that this is what we mean by angular velocity, right?
Yes, sir. Pretty
Okay.
straightforward.
Okay. But here I didn't. Here we have just written some general formula. Okay. What I'm saying is intuitively what you called angular velocity agrees with this definition. So but this is more general. Okay. So this is not to prove. What I'm trying to say is that omega is a property of the frame. Okay. And it agrees with angular velocity in any in simple situations that we know. Okay. Is this point clear? So if you have some arbitrary rotation about some arbitrary axis also, this will happen because P3 is nothing special. We know that. So this, okay, so you need to verify this. Okay, so check the sign, okay. And please let me know. Okay, so whether it is minus omega or plus omega, okay. Because it's also a function of, I could fix that by, putting a minus here and a plus here, okay.
So what you mean to say is that in the previous definition you showed us that a vector exists as that is followed, and in the second example you showed that the vector follows the definition of angular velocity.
Yes, so I'll just call omega, which appears in the first definition itself, as angular velocity.
Okay, sir.
Okay?
Yes, sir.
Okay. Oh, we are doing good. Okay, so now we want to, okay, so are there any questions? This is a good point. Questions, comments, even repeating whatever I said in your own words is fine, some other people may understand better. So, anything? Okay, so the idea here now is so what we have. So what I will do is we'll compute velocity and acceleration in both frames. Okay, so this is where this maths picture is nice. Okay, so what is velocity? Let's just do this. Right? In frame O, this is all that is happening. This is in frame O. But frame okay. But now there's a second term in this thing because the frame is also rotating in O prime. So I still have to do this. I don't know what this cross is doing here, so let me rewrite that. Sorry. Is this clear? So we are getting two variations. One is the variation of the components, but there's a second term which is coming, which looks, which is because the frame is varying. Okay, now we know what di by dt is, so now I can rewrite this like this. Okay? This is the velocity. And what is this? This is just the vector x. Okay, is this clear? So we see that the velocity gets a second term, which we understand, we understand this omega cross kind of term. We understand this, but this comes out very naturally in this. This is just dx by dt in frame. Okay, so the most important remark here is what observer O prime was thinking like a physicist would have said is not the velocity. Because there's an extra piece. Rather not the components of the velocity.
Because it is not covariant under rotation.
No, because it's a non-inertial frame. I mean, that's about it. It's a changing frame. It's a moving. It's a time-dependent frame. So that's a second contribution.
Yeah, I mean in the terms of the definitions that we made.
Yeah, no, it's not something very deep. I mean, usually what O prime will do, O prime will try to say, yes, I'll just call what I want to call velocity is just the dot's time derivative of the position vector. So this is what you want to assume, but that's not quite correct.
Sorry. I was talking about vector.
Okay, so. That's the thing, okay? But of course, if the frames were not changing that way, then this term wouldn't be there. So this is a very important remark. So now we can take second derivative. So acceleration. Let's give it this, let's call this U. Okay, so I just substitute everything. Now we start doing derivatives. And I'll stop after I just take all the derivatives and you'll see a whole slew of terms. Okay, so that is when the derivative hits this. But there's one more term which comes when the derivative hits this. Okay, so I'll jump one step and write it as. Okay, so that's the first thing. Second term will be. Okay, we have to also substitute for U, but all I want to, before I stop here, is that if naively O prime would have said that this is the acceleration, but we see a whole bunch of extra terms, we have to simplify. So these are extra terms. Okay, so we will next lecture we will study these things in this thing in more detail. But I suggest you complete the calculations before tomorrow's lecture, so that we can. So you have to substitute here for U and collect terms which are looking the same, etc., etc. So you should find that there are, I think, 2 times this term will come, and so on and so forth. Okay, so you can check those things. And okay. So, but the thing is that traditional way is you want to make Newton's laws work, which says that you want to always make F equal to ma. I mean, so if you write it as vectors, actually it still holds, But if you try to think in terms of components, the acceleration is not xi double dot. Okay, so, but sometimes people tend to force, which I think is the wrong way to do it, treat this, call this as acceleration, which is not. Just as we saw that xi dot was not velocity. The real velocity was this guy. Similarly, the real acceleration is this whole thing. It's a whole bunch of terms. So what people do is to move these things to the other side, to the f side, and call them pseudo forces. Okay, which is in some level a little bit confusing term. What I'm saying is that the origin is very, very, very nice. And so we'll see what all these various terms mean. Okay, so there's something called the Coriolis force. There is something. Okay, so these are all, when they, whether you call them forces, but they're all pseudo forces, but they're all observable. So the observer O prime will know that he or she is a non-inertial observer because these things are definitely there. Okay, so next lecture we will see how these things work, and I'll also probably comment on why I think several books have confusing formulae when there is no confusion that is needed. Okay, so I'll stop here and pause for questions.
So can we consider omega bar as a time-dependent generator of rotations?
Omega is nothing. No, it's not. It's nothing. Because generator means something very specific in classical mechanics, no? So I wouldn't use that. I mean, it doesn't sound right.
Okay, sir.
Sir, what does this 2 mean below the second term in?
They're all there. I mean, so that is nothing. I mean, it's just this, right? I mean, let's go back to. So this term, you can see my mouse.
Yes, sir.
Okay, so this d by dt, I'm just using a sum of two terms. So first line is derivative of this. Second line is derivative of this. So Leibniz rule will tell d can act on omega, it can act on this. So dx by dt is u, and d omega by dt, I just left it. We'll call it angular acceleration.
Okay, and sir, there should be a prime on x dot and x double dot, right?
Yes.
Okay.
Yeah. Any more comments? Okay, so then let me stop recording.